So last time we tried to introduce the bosonic systems, and the simplest example of the bosons is just a harmonic oscillator, a single harmonic oscillator in quantum mechanics. And I assume that everyone knows this problem and how to solve this problem. And the easiest way and more physical approach is the approach that introduced here, where this harmonic oscillator Hamiltonian is made of kinetic energy. And the potential energy is nothing but Hooke's law, which is 1/2 kx squared. But we can redefine the operators, which is made of linear combination of position operator x and momentum operator p, in such a way that we could define two operators, b and b dagger. If I define this b and b dagger in this way, and I can rewrite this Hamiltonian not in x and p, but in b and b dagger. So b dagger is the Hermitian conjugate of the b operator. So if I do so, you immediately see that this Hamiltonian reduces to a very simple form, which is h bar omega times b dagger b plus 1/2. And later we will define such a b operator as a phonon operator. But in this simplest example of the bosons, which is harmonic oscillator, we could easily solve for all those eigen states, including eigenenergies and wave function of the corresponding eigenstates. And this b dagger b operator, we will define this as a number of bosons or a number of phonons. So the ground state is a state that there's no phonons, and the first excited state is a state where MB is 1, and so on and so forth. So that you could immediately get this eigenenergy E0, which is the ground state energy, which is 1/2 h bar omega. And we know that the ground state energy is not a zero energy. It has a finite energy, and this is called zero-point motion. And once we know the ground state energy, and we can solve the wave functions based on this b and b dagger, and so on. And then when we get one floor higher than this ground state, we get the state, first excited state, with the energy 1 h bar omega higher than the previous lower energy state. In this case, E1 has the energy 3/2 h bar omega, and so on. This E2 is actually 5/2 h bar omega. So the distance between the adjacent neighboring energy levels is precisely 1 h bar omega, and this h bar omega is our phonon energy. So this is another homework. From your quantum mechanics, you could easily verify that this b and b dagger operator satisfy these commutation relations for bosons. So the definition of this bracket is this: b dagger minus b dagger b. Remember, both b and b dagger are quantum mechanical operators. But we know that from quantum mechanics, this x and p satisfy these commutation relations that commutator between x and p is just 1. But this b and b dagger are nothing but the linear combinations of x and p, so you could imagine that this relation also holds. So this is the baby version of phonons in solid state. So we can generalize this simple harmonic oscillator in quantum mechanics to many harmonic oscillator, and they are coupled together like this. So in a realistic solid state, you have many ions, and ions can actually vibrate relative to the equilibrium position. And this vibration mode, you could approximate this lattice vibration by harmonic oscillator potential. Okay, so this is the realistic potential between the electron and ions, whereas the ions can actually make a displacement ui relative to this equilibrium position, and you could have the electron ion, say, potential, where this electron actually is here with the vector capital Ri relative to this original ion position. So that the electron ion potential also changes. So we will derive this later. This is just an introduction to phonon. Okay, so you could actually Taylor expand this yellow curve, which is the electron ion potential, 5x as a function of the real space vector x. So there is the minimum point somewhere in your profile, and this minimum point is nothing but the equilibrium position of the ions, and the ions could fluctuate back and forth relative to the equilibrium position, and so we could Taylor expand this phi and up to second order, and we neglect the first order term because we are sitting very close to the minimum point, and when we are at the minimum point, this first derivative of Taylor expansion vanishes. And if you collect up to second order in this displacement vector u, and this is nothing but a bunch of coupled harmonic oscillator. So this is x and x. This is k, roughly speaking. So you get a bunch of Hooke's potential, 1/2 of k x squared. So you sum over all possible springs, attach the ion like this. So this is what happens in the real solid state system, where this ion can vibrate. So you could consider the ions are just harmonic oscillator, but there are many such harmonic oscillators that could connect by this kind of a generalized potential energy, which is 1/2 kx squared. So this is a many-body harmonic oscillator problem. But you could diagonalize this in terms of normal mode coordinates, which we'll introduce later, and you simply sum over all these normal modes. But for each normal mode, this thing that you sum over is nothing but the single harmonic oscillator that you already solved in quantum mechanics. So we will go through detailed calculations later, but this is just a very brief introduction to the phonons, and phonons are nothing but coupled harmonic oscillator that you are already familiar with in quantum mechanics, and this operator B and B dagger is the first operator that you should know in bosonic language. Okay, so you don't recognize the B and B dagger as bosons, but now we should define this B and B dagger in the second quantized formulation, and you will immediately recognize that B and B dagger are boson operators. Okay, so this is the first bosonic operator that you have encountered, but you did not recognize that they are bosons. Any questions?
不好意思，就是那个 S 跟 P 的 commutator 不是应该是 IH bar？
Right. So if I simply just take this unit, IH bar is 1, so this is in some units, this is 1. Okay? Yeah, you're right. So this is IH bar, but for the B and B dagger, since this I and H bar appears this coefficient here and there, so you get cancellations. So in some shorthand notation, this we simply just normalize IH bar. Since we know the basics of fermion bosons, and let's talk about this elementary excitations. As I mentioned, this is the most important concept in advanced solid state. So let's formally introduce the term called elementary excitations. So by definition, this is the long-lived, low-energy excitations in solids with quantized energy. Okay, so as I already mentioned previously, that at very low temperature, close to zero temperature, most all the solid state materials would have low temperature or low energy excitations with definite energy, which are quantized. And these quantized low energy excitations are called elementary excitations because it's our elementary particles. Like a high energy physics, we have elementary particles like quarks and gluons, but here in solid state, our elementary particles, these excitations. So phonons are part of this elementary excitations, which I will describe in more details later. So oftentimes we have two different categories that belong to elementary excitations in literatures. The first class is called quasi-particles, and conventionally this refers to the electron hole excitations or fermionic excitations. And in particular, when we call this quasi-particles, in the literature, it refers to this electron hole pair in the presence of a weakly interacting electron gas. So you could understand this from this cartoon picture, which we already introduced last time, that at very low temperatures in the ordinary metals, we have a Fermi spheres and Fermi surface. Okay? But at finite temperatures, there's a window above and below the Fermi surface of the order of kBt, where electrons inside the Fermi surface could get out of the Fermi surface and become steady-state electrons. And so we have this electron hole pair excitations like this. So this is hole and this is electrons. So some electrons right below this Fermi surface, because of the thermal excitations, can actually get excited to the excited states within this thin shell above the Fermi surface, and this electron is occupying this excited states and leaving behind a hole right below the Fermi surface. And this is what we call this quasi-particles as elementary excitations in metals, because at low temperatures there are not so many that electron hole pair excitations, only a handful that you can count by your fingers. Okay, so very, very few electron hole pair exist in ordinary metals at very, very low temperatures. So only a handful electron hole pair excitations when temperature is very, very low but finite. At the same time, these electrons suffered from Coulomb scattering. So imagine we have another electron hole pair somewhere here, and we also have some electrons within this Fermi surface, and these electrons below and above the Fermi surface with the relative thin shell, kBt, they should interact by Coulomb interactions. So there's a Coulomb. In such a situation, we can still call this elementary excitations, and this is due to the so-called Landau's Fermi liquid theory, which we will introduce in just a moment. Okay? And we will discuss this electron hole pair excitations in the presence of Coulomb interaction in just a moment. But here is one example of what we call the quasi-particles, namely electron hole pair within the thin shell of the Fermi surface of the order of kBt at low temperatures. And this electron, excited state electrons, are fermions, we know that. So we call this quasi-particles. So there is another class of elementary excitations which we call the collective excitations. So the purpose of this course is to analyze the elementary excitations in solid-state materials, and there are fermionic elementary excitations and also bosonic elementary excitations. And we should find a way to count those quasi-particles or collective excitations. And once we can count them, we know their effects and we know how to describe the transport and thermodynamic properties of solids. And the way to count this is by second quantizations. So let me continue. So the second class of elementary excitations are called collective excitations. And in the literature, they refer to the bosons or bosonic excitations. And the examples of those bosonic excitations are phonons, plasmons, and magnons. So the collective excitations refer to the fact that these excitations are many-body effect, where many particles show some kind of a collective phenomena. Say, for example, in the phonon case, that all ions vibrate, in the same frequency, Okay, so that you get a phonon, which comes from not just a single particle excitations like electron hole pair, you get collective excitations like this, meaning these excitations consist of many particle states, and they all contribute to this low temperature, low energy excitations. Like everybody moves, it's not just a single particle that get excited, but all particles get excited. Okay. And so this is a many-body phenomena, namely this phonon phenomena is the simplest example of the many-body physics, in the sense that all the ions vibrate at the same time, and they are all coupled together. So this is just convention in literature that we call bosonic excitations, collective excitations. Okay, so we will see another example of this when we talk about these magnons, the spin waves. Again, all the spins actually are doing the same dancing or same excitations, so that you could have this Magnon excitations. In other words, this Magnon or spin wave excitations are contributed from all spins on the lattice. So in other words, these magnons or phonons or plasmons are not just single particle physics, but many particle physics, and we will second quantize all this Hamiltonian of this bosonic system and see how we could see that this is a many-body effect. Of course, this is the bosonic collective excitations. Again, their excitation energies is quantized, right? So just like this case for phonons, right? So you get omega. This B-dagger-B operator count this phonon number, so you can actually get all these excited states by simply counting your number of bosons or number of phonons. So all these collective excitations have this common features that their excited state energies are all quantized. And the reason why you get such excitations are because of this collective motions or this kind of many-body phenomena. So the purpose of this course, or the goal of this course, is to analyze these quasi-particles and also collective excitations in a systematic way and by second quantization approach. And the reason why we apply the second quantization is because we have not so many such quasi-particles or elementary excitations, because we only need to deal or to count a handful of those elementary excitations. So there are not so many that excited state quasi-particles, only a handful, so we can, for the time being, forget about all these other particles that are not coming to play, but we only focus on those quasi-particles that, for example, close the Fermi surface at low temperature and so on and so forth. And this is the way that we could understand this interesting many-body phenomena at low temperatures in solid-state materials. Officially, we are entering this advanced level of a solid state right now, because these elementary excitations and quasi-particles are the essential concept in solid-state physics. So let's look at this quasi-particle first, meaning electron hole pair in ordinary metals. And as we already pointed out, that we get electron hole pair excitations. And now let's just look at the effect of, say, Coulomb interactions on these quasi-particles. But before we introduce, let's talk about this very famous theory called the Landau's Fermi liquid theory. So in 1950s, Landau actually developed the theory called the Landau Fermi liquid, and which is a very intuitive way of understanding weakly Coulomb interacting electron gas in metals. And this theory successfully explained most ordinary metals. And the essence of this Landau's Fermi liquid picture is precisely based on the non-interacting Sommerfeld electron gas. So let me just formally introduce this. It says that in Coulomb interacting Fermi gas, so all the physical properties of this Coulomb interacting Fermi gas, assuming that the Coulomb interactions are not so strong, is a weakly Coulomb interacting Fermi gas. Okay? So in such a case, the electronic properties of those Fermi gas looks almost the same as non-interacting Sommerfeld electron gas, except we need to renormalize some parameters such as dispersions, effective mass of electrons, and so on. Okay, so as the interaction turn on very slowly or adiabatically, so adiabatically means very slowly without suddenly disturbing your system. So if you turn on this Coulomb interaction very, very slowly, and this Pauli principle so makes this ground state of this system unchanged. So the ground state is actually occupied state, namely all the states within the Fermi surface, all these electron states within the Fermi surface at zero temperature are still the same. So even in the presence of the Coulomb interaction, as long as you turn on the interaction very, very slowly, however, the electron kinetic energy and electron mass or ion mass will get renormalized. Kinetic energy still follows the free electron kinetic energy, which is quadratic in K, h bar squared, K squared divided by 2m. However, this little m here is not the free electron mass, but renormalized electron mass. So electron-electron Coulomb interactions in almost free Fermi gas system under this Landau's picture, this kind of weakly interacting electrons still show the same kinetic energy, the same form, quadratic in K, but just this effective electron mass get changed or modified, and you get a heavier electron mass compared to the non-interacting electron mass, and this is called electron mass renormalization in Fermi liquid, and also this ion mass will get modified. So these are the only changes that you need to update. Other than that, this weakly Coulomb interacting electron gas is the same as non-interacting Sommerfeld electron gas. Okay, so this is a very, strong statement, a very powerful observations that in ordinary metals where the electrons are very weakly Coulomb interacting, okay, in that case, we can still use the Sommerfeld free electron gas model to describe such metals, ordinary metals, except now we should renormalize those parameters. Okay, most of those parameters that we should update are just electron mass or ion mass. So let me just make a correspondence between this Fermi gas for non-interacting electrons and these quasi-particles in the presence of weakly Coulomb interactions, and get shifted by m star and electron mass, energy, and therefore these quasi-particles that we just defined over there as the excited state electrons are very close to the Fermi surface, but in the presence of Coulomb interactions. Okay, so in such a case, this electron-hole pair excitations, or those excited state electrons, still follow the same quantitative features for the Fermi gas or non-interacting electrons, except now you should just simply modify their mass and dispersion. There's a very important difference between this Fermi gas and this quasi-particles is the lifetime. So in the free electron gas or Fermi gas, elementary excitations or quasi-particle excitations live forever, almost forever. So which means that suppose I just encircle this, and I call this psi electron, free electron gas. So if you compute the wave functions at different times, so say psi free electron gas at different times, So this is the transition amplitude if you simply just follow the time evolution of such excited state electrons in a non-interacting case, and you get always a finite value. So this is always non-zero. Okay, no matter how long you wait, and if you calculate this probability transition amplitude, then for free electron, guess the excited state electron are always there. So once it is there, and it won't go away. However, suppose these excited state electrons suffer from the Coulomb interactions, and the story is different. In such a case, if you consider the Coulomb interactions among those excited state electrons, then you get Coulomb scatter, and after the scattering, some electrons in the excited states will actually fall back to this states within the Fermi surface. So the quasi-particle or this excited state electrons decay. Okay, so you get a decay time. So the lifetime for weakly interacting quasi-particles is actually finite. However, in the non-interacting case, the excited state electrons live forever, meaning there is no decay of your excited state electrons, but in the presence of the Coulomb interactions, your transition amplitude carry a decay factor. So in the presence of Coulomb interactions, the excited state electrons cannot live forever because the energies epsilon theta of k is actually carry an imaginary part. And this is called, self-energy, imaginary part of the self-energy. So the Coulomb interacting electrons' energies actually carry an imaginary part, and that imaginary part will lead to a decay of these quasi-particles over time. So when time goes to infinity, this transition amplitude vanishes, which means that in the presence of Coulomb interactions, those electron-hole pair do not live forever. Or they have a finite lifetime. Okay, like human beings. If you wait until infinite amount of time, then these excited state electrons will actually get scattered by Coulomb interactions and longer exist in the long-term limit where time goes to infinity. And the reason why you get a decay of your quasi-particle is precisely because of this Coulomb interactions. So the most dramatic effect of the Coulomb interactions in the weakly interacting Fermi gas is the lifetime, because those electrons can actually get scattered by Coulomb, and when they get scattered, some of the excited state electron will actually fall back, and therefore the original excited state electron is gone because it decays to other states. So those quasi-particles show a finite lifetime. So based on this Landau's Fermi liquid picture, after the break, we will address this. The first non-trivial consequence of this Fermi liquid is the resistivity, electrical resistivity of the ordinary metal at very low temperature. It actually vanishes as temperature square. And we will use again this cartoon picture without much of the calculation. We can immediately get the statement that the electric resistivity of ordinary metals vanishes in the t-squared fashion, and which is one of the most successful predictions by Landau's Fermi liquid. And this behavior is actually confirmed experimentally. And this is called Fermi liquid resistivity. And let's take a short break. When we come back, we will study this behavior. Let's talk about quasi-particles. So as I just mentioned, this the lifetime of this quasi-particle in weakly Coulomb interacting electron gas is finite. It's not infinity. And this leads to this very well-known results that the electrical resistivity of ordinary metal vanishes as T squared when temperature is low enough. So let's just derive this result. And let me draw again this thin shell above and below the Fermi surface, and you get the Fermi momentum. And suppose we have two electron states labeled by epsilon 2 and epsilon p, where epsilon 2 is the electron right below the Fermi surface, and epsilon p is the electrons right above the Fermi surface. And we know that epsilon p is coming from the occupied state, but gets excited to the excited states by this quasi-particle excitations. So we assume that there exists some excited state electrons already, and this electron can actually interact with the electrons within the Fermi surface, and they could get Coulomb scattering like this. And so the outgoing electrons carry different momentum, which we call this epsilon 3 and epsilon 4. And it's by Pauli principle, this epsilon 3 and epsilon 4, most likely will live outside of the Fermi surface. Okay, remember, most of the states within the Fermi surface are almost occupied, except some vacancies that are present because of this electron hole pair excitations, but there are only very few vacancies here. And apart from these very few vacancies or holes, and almost all electrons within the Fermi surface are fully occupied. And likewise, in excited states, almost all states are empty because of this, states are above the Fermi surface, except there are only a very few states which are occupied like this, but all the other states are completely empty. So these two electron states can actually get Coulomb interaction, right? Okay, so of course the electrons out of the Fermi surface can also Coulomb interact with the other outsiders, right? Excited state electrons, epsilon 3 or epsilon 4, epsilon 5, but this probability is really, really low. Okay, so the initial state, suppose it's epsilon p and epsilon, say, n, where epsilon n is actually above the Fermi energy, and this kind of scattering is really carry very, very low probability because both states are almost empty, right? And likewise, the initial state, suppose I choose two occupied states, epsilon 5 and epsilon 6, which are all within the Fermi surface, and this kind of a scattering process is really not likely to occur because all the states within the Fermi surface are really stable, okay? Because they are stable. Therefore, the most likely scattering between electrons are the electrons, coming from one electron comes from the outsider, another insider. Okay, so these two electrons, one within and one out of the Fermi surface, is a scattering process which dominates all this electrical resistivity or scattering of electrons. But once these two electrons get scattered, the outgoing electrons could be anywhere, right? It could be two outgoing electrons, say, all within the Fermi surface, or one within one out of the Fermi surface, or two, excited scattered electrons are all out of the Fermi surface. But again, if you look at this probability of these three different possibilities, that one is epsilon 3 and epsilon 4 are all out of Fermi surface, and one in and one out, or two in. So these are all the three possible scattered electron states, as we just noticed that because of Pauli principle, and almost all states that are inside this Fermi surface are almost occupied, and almost all states above the Fermi surface are empty, and therefore the a scattered electron can actually occupy almost all empty states, that is most likely to occur because there are many, many states available. So this is favored because the outgoing electrons, states could actually occupy any place they want out of the Fermi surface. So one in, one out, or two in are not likely to occur because, again, the states inside the Fermi surface are almost occupied. Okay, so from this scattering probability point of view, the first situation is more likely to occur because you have more states available. But they should satisfy this energy conservation. So let me just rewrite this initial and final state. So initial state, we have epsilon p, which is above the Fermi level, and epsilon 2, which is below the Fermi level. And after scattering, epsilon 3 and epsilon 4 are all above the Fermi level. So this is the Coulomb scattering, which this process is actually the dominating scattering event. Is this kind of situation here? Okay, but we know that the energy should be conserved, meaning epsilon 2 plus epsilon p should be equal to epsilon 3 plus epsilon 4. This is energy conservation. Okay, so let's estimate this lifetime or scattering probability or scattering rate. So the scattering rate of this Coulomb interaction is actually proportional to two things. One is the number of available states and also the number of empty states. So the number of available states gives us the estimation of how many initial states that we could have such scattering processes, which is proportional to the scattering probability. But that's for initial states. But the final state, probability is actually proportional number of empty states that the scattered electron can occupy, right? So the full scattering rate is actually proportional to the product of these two numbers. So the total probability is proportional to the number of available states times the number of empty states. So that's just a rough estimation, but we have this energy conservation among these four electron states. And this is a constraint, but we also have these kind of constraint that epsilon p is above, epsilon 2 is below the Fermi surface, but epsilon 3 and epsilon 4 are all above the Fermi surface, which leaves us just two independent degrees of freedom, which is number of available states and also number of empty states. So let's just estimate this number. The number of available states is the states that inside the Fermi surface, right? Well, let me just plot this again once more here. So the number of available states for initial states is the area of volumes inside this Fermi surface with the width of kBt. So the volumes or areas of the thin shell within the Fermi surface is proportional to the number of available states, right? Because almost, you could actually pick any one of the states as your initial states. So this number of available states is actually proportional to the volume of the thin shell. And the volume of the thin shell is proportional to kBt because this is the width of the thin shell, right? So likewise, you could estimate the number of empty states. The number of empty states is also proportional to the width of this thin shell, which is again kBt. Remember, when we make the plot of this Fermi function, and zero temperature is actually show a step-like jump from the fully occupied state to the almost completely empty states. So that's the perfect step function. However, at finite temperature, you get a smooth crossover of the step function, and so some of the electrons inside the Fermi surface are gone, and they are going out of the Fermi surface. Okay, but the number of electrons that get excited to the excited states is actually proportional to the width of this crossover. scale, right? So, and the width of this inner shell and the outer shell are of the same order of magnitude, which are both kBt. So that's how you draw this, this Fermi surface. So this is inner shell, and you also get the outer shell. So both inner shell and outer shell regions show the same order of magnitude, which are both order of kBt, relative to the Fermi surface. So the volume of this two-thin shell is actually proportional to kBt, but of course there's some minor factors regarding to the other dimensions, but we don't care too much because temperature is so low that this thin shell is really, really tiny, really thin shell. So we can forget about all the other differences between this inner shell and outer shell volumes, and the leading order of this volumes of the two thin shell are both of the same order of magnitude kBt. Right? Okay, so therefore the scattering rate of these processes is actually proportional to the product of these two numbers. And we also know that the electrical resistivity is actually proportional to the scattering rate. Therefore, we immediately get this electrical resistivity of the quasi-particles at low temperatures is actually proportional to T squared, and that is precisely what we know for the electrical resistivity of ordinary metals when temperatures is almost zero. Okay, and this is the success of this Landau's Fermi liquid properties for ordinary metals. So you don't need to solve the Schrödinger equations, and we don't need to consider second quantization, but just from the statistical mechanics and scattering rate or scattering probabilities, and also this kind of low energy elementary excitations of this weakly coolly interacting electron gas, you could immediately see that this 1 over tau is proportional to T squared. And of course there's some prefactor, okay? But apart from this prefactor, you get qualitatively this behavior, and this behavior has been confirmed experimentally. Okay? So now you could go back to your Kittel's or Ashkerf Mermion and you determine the prefactor. A more precise estimation, derive more accurate estimation of this 1 over tau, which is kBt squared times pi squared h bar squared mkf squared. So in other words, you could check your introductory solid state textbook on this part and to really more accurately determine the prefactor, which is given by this red box, pi squared h bar squared divided by m times Fermi momentum and everything squared. So this is the more accurate estimation of this 1 over tau apart from this kBt squared. So I can give you some numbers. Some metals actually typically is 1 over tau or tau all of 10 to the minus 10 seconds at room temperature. So you could check your solid state 1 textbook and estimate these numbers. So let me just make some comments and remark. So the initial states I assume here is epsilon p is above the Fermi level, epsilon 2 is below. But what happens if I use a different initial states which are exactly at the Fermi level? Suppose I choose these two initial states where both of them are exactly at the Fermi surface. And what happens if I do so? If I do so, then there's some consequence of this. So let me just sketch what happened here. So if both epsilon p and epsilon 2 are precisely at Fermi surface. So by energy conservation, if I assume these two initial states are precisely at the Fermi surface, and then the sum of these two energies are just 2 times epsilon f, right? But this has to be the same as the sum of these two outgoing electrons, epsilon 3 and epsilon 4. But again, if I assume epsilon 3 and epsilon 4 are both out of the Fermi surface, and this energy conservation cannot be satisfied if both epsilon 3 and epsilon 4 are both above the Fermi surface, and therefore there's no such a scattering between these two electrons exactly at the Fermi surface and two outgoing electrons above the Fermi surface. But what happens if both epsilon 3 and epsilon 4 are exactly at the Fermi surface as well? Of course, this is one possibility, right? So all the 4 states are exactly at the Fermi surface. If that occurs, you could actually calculate again this scattering rate or scattering probability, and you know that this probability is actually proportional to what? The area of the volume of the inner shell, but it's not the inner shell, it's exactly at the Fermi surface. So the volume of the Fermi surface is 0. Number of available states is actually almost 0. Likewise, the outgoing electron states have a probability which is proportional to the outer shell Fermi volume, but the outer shell volume is also empty, almost 0. So you got 2 0, almost 0 numbers and multiply together. So if all the 4 states are precisely at the Fermi surface, and there's no way that you could have a Coulomb scattering, which means that the probability of a scattering is actually 0, which means that this quasi-particle are living forever if they are exactly at the Fermi surface. So let me just make a remark here. So suppose the 4 states are exactly at the Fermi surface, then tau goes to infinity and 1 over tau goes to 0. So there's no scattering of electrons if 4 of these 4 states are all exactly at the Fermi surface. So lesson here is that if we consider only the states that on the Fermi surface, then those electron states are protected by this Coulomb scattering, and there's no scattering at all if the states are exactly the Fermi surface, and therefore this so-called quasi-particle live forever. But there's no quasi-particle in that sense, because by definition the quasi-particle is defined by electron-hole pair. But if all these 4 states are exactly at the Fermi surface, then how to define this hole and electrons, right? So you may consider there's a hole, but there's another electrons, but they're all exactly at the Fermi surface. So the concept of quasi-particle actually breaks down. But nevertheless, this is the lesson that we all know, that the states that right at the Fermi surface are very stable. However, the states below and above the Fermi surface, they are not stable, because they could get scattered by Coulomb interactions like this, and this kind of a Coulomb scattering processes will lead to the T-square resistivity. Therefore, in the presence of Coulomb interactions, only the states that exactly at the Fermi surface are stable, and other states are not stable, and they should decay. The way that they decay is that they could get scattered by Coulomb interaction over there, and therefore the original excited states, electrons, are gone. For example, this epsilon p, after scattering, this becomes, for example, epsilon 3. So this state is gone after scattering, but you get another state, epsilon 3. And therefore, if you just look at this time correlations between epsilon p states at initial time equals 0 and final time equals t, then at some time later, so this epsilon p state is gone. So that is called this lifetime, finite lifetime of a quasi-particle. Because of this Coulomb scattering, the lifetime of the quasi-particle is not infinity, but finite. However, the states exactly at the Fermi surface are free of this Coulomb scattering, so they could live forever. But this is already there because all the states that within the Fermi surface are all occupied, and so in some sense, these electrons on the Fermi surface are very stable states. And suppose there's no Coulomb scatterings, and all the states are stable, right? Because they cannot get any scattering processes. But Coulomb interaction really lead to such scattering processes and lead to T square of a resistivity. So I suggest that you should really remember this cartoon pictures and imprint these pictures in your mind and your brain, your head, so that whenever you read the papers or books or references, they talk about the quasi-particles, and you should immediately pump up this picture over here. So I should emphasize that not just solid-state physics, but all branches of physics should be understood in terms of physical pictures or diagrams or plots or graphs. Okay, so this is the diagram that explains all the physics. So you should get used to learning physics by drawing the cartoon pictures or diagrams or diagrammatically or graphically approach to understand this physics. Great. So that's all about this fermionic quasi-particles in the presence of weak Coulomb interactions. So let's take a short break. When we come back, we will continue deducing all the thermodynamic properties of Fermi liquid. So I think this is not difficult to understand, but it's not trivial either. Even though there is no complicated mathematical equations or formulations, but this kind of cartoon picture contains a very rich physics which takes time to really digest and to think about. So far, we just used a simple hand-waving-like estimation on the electrical resistivity of ordinary metals in the presence of Coulomb scattering, but this kind of a hand-waved argument, is not so useful if you would like to understand other properties more accurately in terms of a quantitative understanding, and to include the Coulomb interaction effect in Sommerfeld electron gas, we need to introduce second quantization. Okay, but before we introduce this, let me just summarize some of the predictions made by non-interaction Sommerfeld model and the deviations of those Sommerfeld naive predictions from the real experimental data. Okay, so let me just remind you this Sommerfeld electron gas and its limitations. As we already showed many times, that this free electron gas in 3 dimensions lead to the Fermi sphere, and the Fermi energy is defined this equation, and the number of electrons is actually 2 times this Fermi volume, and this is simply just the sum over your k points. So each k point on average occupy a little cubic volume, and you simply just calculate the volume of this Fermi sphere and divide it by this average little cube, and therefore you know how many dots are there. And each dot represents just electron level, energy level, but each energy level can occupy 2 electron states with opposite spin, so this factor of 2 take care of the spin. So you could define the number density, which is V 3 pi square kF cube. So then the kF Fermi momentum could be estimated as 1/3 power of this 3 pi squared times this number density, which is defined by the total number of electrons divided by the volume in real space. So you could just write down those numbers in the standard convention, where electron radius is defined by this 1 over this electron density. So R0 is called electron radius. It's the average distance between 2 electrons, which depends on the number density, right? And number density is the function of a Fermi momentum. So R0. And so this average electron radius could be expressed in terms of the Bohr radius. So Rs is the length scale in units of Bohr radius, where Bohr radius A0 is 0.5 angstrom. So this Rs is actually dimensionless constant, which measures the electron radius in units of Bohr radius. So for many metals, this Kf dotted R0 is about 1.9, or Kf has this units, and most metals have this Rs somewhere between 2 and 5, and Fermi energies somewhere between 1.6 and 12.5 electron volt, and the Fermi momentum somewhere between those numbers, inverse of Armstrong. So that's just a rough estimation of those parameters for ordinary metals, and this epsilon F is actually this. So all these numbers are from the Sommerfeld free electron gas, and Ry is called first ionization energy. Okay, so these are the predictions from the Sommerfeld electron gas. Let's look at how good this Sommerfeld free electron gas is when we talk about this realistic experimental observables. So let's look at first the specific heat or heat capacity. So Cv is defined as temperature gradient of the internal energy, but this internal energy at finite temperature for a free electron is estimated again by this plot. So at finite temperature, with a finite width of order of kBt, both below and above the Fermi level, where the electrons below the Fermi surface will get excited and to occupy the states above the Fermi surface. And the total number, say, internal energy change at finite temperature could be estimated by the product of average single electron kinetic energy per electron, which is kBt, multiplied by the number of electrons. And the number of electrons here is actually the density of states at the Fermi level multiplied by, again, the area of that energy range. And so this is kBt, which is the width of that range. And so this is estimation of the total energy change, and you could just take the ratio between these two. So Cv is actually partial U, partial T. So let me finish this, and then we end this lecture. Okay, so you can see immediately that the specific heat is linearly proportional to temperature with a prefactor over here. So the more exact calculations is this, which is this. But the experimental observations of Cv is given by the same linear in temperature behavior, but with some different electron mass. And next time we will compare the predictions from the Sommerfeld free electron gas and the experimental observation of this specific heat and for different metals, and you'll see that there are some deviations between these two, which suggests that the Sommerfeld electron gas model, although simple and useful to understand many simple metals, but is not enough to capture the Coulomb interaction effect. So there's no hand-waving argument for the specific heat in any theory anymore. Okay, the Landau's Fermi liquid theory can only describe this to some extent, and the Sommerfeld electron gas is not that useful to accurately capture this thermodynamics of ordinary metals. And because of this insufficient theoretical tools, we need to invent a more accurate and systematic way. And after we comparing these experimental observations to the Sommerfeld predictions, then we could formally define the second quantization. So the way out is to really count the quasi-particle numbers by introducing creation and destruction of single particle, okay, out of a many-body system. So that's the departure from the elementary or introductory level of a solid state. From now on, so we formally enter the advanced topics of solid state physics. So that's enough for today. Okay, so we'll continue next Monday.